Hey guys, welcome to section 8.5. Let's get started with our lecture. Quick note beforehand, I do have a little bit of a runny nose cold situation. So if I'm sneezing or blowing my nose, I apologize. Try and keep it off camera. So last section we talked about parametric functions and parametric equations as a way to graph functions differently than the standard rectangular functional way. And so when we say rectangular, what we're really talking about is the rectangular grid system, which is still the same grid that the parametric system uses. The difference being that the parametric system really kind of has three variables. It has the input variable t, and then the two output variables x and y. Whereas the rectangular system just has an input x and an output y. The polar equation system is similar to the rectangular in that it only has an input and an output, but our inputs and outputs are different. Okay, and so first, let's talk about what it uses. It uses the letters r and the Greek letter theta instead of x and y to locate a singular point P. And what we have to first do is kind of differentiate the way we talk about the axes as well as kind of the whole grid system. The origin, the point 0, 0, as we normally call it, is called the pole. Okay, and the polar axis is what we'll call it. The polar axis corresponds to the positive x-axis. So the way we graph a point, okay, is we can consider these, right? So this axis here, this is the polar axis, right? We've got our pole right here. And so the way it works is theta tells us what the angle is. This angle is theta here, and then this distance is r. Okay. So the theta tells us the rotation in standard orientation, right? So it's 0 being at the positive x-axis, going counterclockwise for a positive angle, clockwise for a negative angle. And r tells us the length of kind of the distance from the pole to the point, if you will, kind of like a radius of a circle. And so the first thing I want to do is I just want to get a little more comfortable plotting these points. Okay. Some are in one's in degrees, the most of them are in radians. Again, it's something to be very careful with when you're dealing with your calculator, is understanding whether you're dealing with an angle in radians or degrees and make sure your calculator is in the correct mode. So here, this first one asks us to plot the point, the polar coordinate, 5, 180 degrees. So we need to go 180 degrees, and that is all the way around to the negative x-axis. Then we want to go 5. Then our r is 5, so we need to go 1, 2, 3, 4, 5. So then this is our point. Okay, and so this right here is the point, 580 degrees. Okay, if we look at this next point here, 7 pi over 6, that is a little beyond 180 degrees, so about here-ish. And we're going out 4, so that's roughly here. Okay. The thing with polar grids and polar coordinates is unless you're given a polar graph, which we'll see that in just a little bit, it can be really hard to accurately depict where these points are just by sketching them. But by sketching them, we can get a rough idea of kind of what's going on. So the next one here wants us to do -4 7 pi over 6. Now, r is, we think of it typically kind of, I related it, it's kind of like a radius, right, of a circle. And a radius is a distance, and it can't be negative, but r is just an r, it's just a value, so it can be negative. And so what happens then is exactly what you would kind of think. If you just think being on the x-axis, okay, positive values would go out along our angle, negative values go kind of backwards. And so here, again, we're dealing with the same angle. So again, we're dealing with this angle that takes us to about here. Okay, and I'm going to put in blue, I'm going to put this angle in just roughly about this. So then in green, that means anything out here. So let's blue. So let's say 1, 2, 3, 4. But since we're dealing with a negative r value, we're going to go and take this angle backwards. 1, 2, 3, 4. And so that means our point is actually back over here. Okay. Now our next point, D, is asking us to do a positive r value at a negative angle. So just like we would when we were dealing with angles on the unit circle and so forth, right? A negative angle just simply means instead of going counterclockwise, we go clockwise. So this one just ends up about here. So we have this this is our angle, 1, 2, 3, 4. So that means our point is right there. Same thing going negative, right? We're going to do the same exact kind of process. This is our angle to about here. That's a kind of positive version. The negative version goes back this way. 1, 2, 3, 4. Okay. And lastly is 4, 5 pi over 6, which 5 pi over 6 is about here. 1, 2, 3, 4. We get this. Now notice that D and F are the same point. So it's really kind of nice and simple. And it kind of helps us figure out, or it helps us to see that different points can really just still be the same point, right? And that makes a lot of sense when we think about collinearity, right? So in other words, points, something being collinear, right? So if you guys remember what that means, right? Two angles are collinear if their terminal side is the same. So if two angles are collinear and they have the same r value, those are going to be the same points. But even more than that, we could have negative angles and positive angles. We could have two positive angles, but we could have a negative r value that would make us all the same. And so there's a lot of ways. So we can actually kind of make a set of equal points here based on these. And we can see that the point 4, 5 pi over 6 is equal to the point 4, negative 7 pi over 6, which is actually equal to the point negative 4, negative pi over 6. Okay. And so negative pi over 6, so I'll do this in a little bit of red just on this last one. Negative pi over 6 would just be this little bit here. So we would have that would be our negative pi over 6 angle. And then you go backwards, 4, taking us to the same point. So there's lots of different varieties and different ways you can write those points. So making sure you're careful. And so you just want to make sure you're kind of being aware of what you're doing there. So if a point has a rectangular coordinate xy and a polar coordinate r theta, then we can relate them using good old-fashioned triangles. Okay, and that's what we're going to do. Okay, so just for example's sakes, we're going to stick in the first quadrant. That just makes our lives easier. So if this is our point here, and so this is the angle theta, this is r and theta, okay? Then the x, so this is x, this is our y value, right? So we can think of this as the point x comma y, also the same as the point r comma theta. Now it's really easy to be like, oh, so x is r, y is theta. Absolutely not. But what we can say is that this side here, let's say it's in green, okay, this side here is going to be r sine theta, and this side here is going to be r cosine theta. Now, if you notice, that means that very simply, we can have a very simple statement that x is equal to r times cosine theta, or is equal to r times sine theta, and since that's a right triangle, x squared plus y squared equals r squared. Now, the only thing we're missing is theta, right? And you can be like, well, if I know x and y, I can use, inverse cosine and things like that. But we can actually be a little simpler, right? Rather than having to say, well, if x is our cosine theta, then we can figure out what r is using our y value and do all that. We can just simply say that the tangent of theta is equal to y over x. And so we get a nice simple relationship going on like that. Okay, so what I want to do is I want to do a couple examples where we're going to convert these points from polar coordinates to rectangular coordinates. The first thing to do is to identify what your r and your theta are, what your r is and what your theta is. So this problem here, that's our r, that's our theta, nice and easy. So our x is going to be r cosine theta, which is just 5 times cosine of, I hate when everybody hits like that, 180 degrees. Cosine of 180 degrees is -1, so this is just 5 times -1 is -5. Now our y value, our sine theta, which in this problem is 5 sine of 180 degrees. Sine of 180 degrees is 0. So we get y is 0. So we get that if we're dealing with 0.5, 180 degrees in polar, the rectangular equivalent is the point -5, 0. It's actually a 3 times pi over 3. Okay. So again, we're just going to do the exact same thing. So x r cosine theta is 3 cosine pi over 3. Cosine of pi over 3 is 1/2. So this is 3/2. So y is r sine theta, which is 3 times sine of pi over 3. Sine of pi over 3 is root 3 over 2. 3 times root 3 over 2 is root 3, or 3 root 3 over 2. Nothing too crazy, right? I'm hoping you guys are very comfortable and quick at evaluating things like cosine and sine of 180, cosine and sine of pi over 3. Both of those angles are on a unit circle, so you should be able to grab that, look at it, boom, be done. So that means that the polar point 3 comma pi over 3 is equivalent to the rectangular point 3/2 comma 3 root 3 over 2. All right. Now, remember we had some kind of conditions, right? Or not conditions. We had some kind of really easy equality things, right? If we look here, we have the 4 comma 5 pi over 6, same as 4 negative 7 pi over 6. And so we can actually say, given the point 1 comma square root of 3 in rectangular coordinates, we can find r and theta that satisfy different conditions. Okay, so both a and b are finding the same point. They're just finding the same point in two different ways. Okay. The first thing to do is find r. And we know that r squared equals y squared plus x squared, or x squared plus y squared equals r squared, whatever you want to say. Very simple, very simply put. So because this problem wants r greater than 0, then we can just simply say that r is equal to the square root of y squared plus x squared. So that's root 3 squared plus 1 squared, which is 3 plus 1, square root of 4, is 2. So r is 2. Awesome. Now, to find the angle, well, we know that we can find the angle by saying tangent of theta is y over x. So tangent of theta is y over x. So that means tangent of theta is root 3 over 1. Means theta is inverse tangent of root 3. For those of you guys that are unfamiliar with the unit circle and unfamiliar with those tangents, which I told you to write down, and we did, we wrote them down a couple times, this is 60 degrees. Right? Notice the requirements for theta was that it's between 0 and 360 degrees. So we are using degrees here. Inverse tangent just gave us 60 right off the bat, so we're good. If our tangent had been negative, right? So remember, recalling back, negative pi over 2 is less than inverse tangent of x is less than pi over 2, right? What that's just saying is that inverse tangent gives us an angle over here. If this had given us an angle right here, let's say it gave us this value here was, let's say 20 degrees. Because the problem wanted us to find something between 0 and 360, we would just say, okay, well, if that's 20, what's that? Right? In this case, that would be 340. So we just have to kind of think about these sometimes, right? See if the initial problem initially gives us an answer that fits the conditions we're needing. If it doesn't, maybe draw a picture to kind of visualize what's going on and see if we can't work to figure out what the answer is within the conditions we need. So the next part, B, says we're still finding the same equivalent rectangular point, but the difference is now it wants the angle between negative 360 and 0 degrees. Our R value is still positive, so our R work is already done. R is 2. Let me give a final answer here. So this point is 2, 60 degrees. R is 2. So to find theta, well, what I know, okay, is this point, 1 root 3, is about here. Okay, and if I make the angle, that angle right there is 60 degrees. So to figure it out as a negative angle, we just simply think, okay, so a negative angle would go like this. Well, if that negative angle and the positive angle will make a full rotation, that means it sums up to 360, so we can do some kind of mental math, and we get very simply that our theta is equal to 60 degrees minus 360 degrees, or it's 300 degrees. So we get the point 2, negative, sorry, those are negative, that's negative 300 degrees. All right. Very nice and easy, hopefully. Hopefully these aren't too crazy, too challenging. But we're not done. Same example continued, okay? Now, what if I want R to be less than 0? Okay, so we know what R had to be as far as using the square root piece, but now we want it negative. So we know then that simply R is going to be negative 2, and that's both of these two problems. Okay, now it would be lovely to just simply say that it's the flip, right? So it's like negative 2 and negative 300, but that's not correct. So again, if we think about where this angle is, we're right here, we're at 60 degrees. That was giving us a positive 2. So 1, 2, here's our point. I need to find what's this angle here. And to find that angle is in a positive manner, we take 60 and we add 180 degrees. So then theta is going to be our 60 degrees plus 180 degrees, which is 240. Okay. Now, again, we want it to be negative, so I'll draw another picture. We had our negative 300 degrees. to get to this point here, but we still want the negative value, okay, we could add 180, but we could also think of this as taking the 60, but instead of adding to go positive, if I subtract 180, I get where I want to be. So our theta here is just the 60 degrees minus 180 degrees, which gets us to our lovely negative 120 degrees. So this point is negative 2, negative 120 degrees. So there's 4 different polar coordinates that are all equivalent to this one rectangular coordinate. Now that could be a benefit or a downside depending on what you're doing and what you're dealing with. It really just kind of depends on what you're going for. So let's make a table of values and sketch the graph of each polar equation. Okay, so this right here looks totally different. You're like, whoa, what is this big circle thing? That is a polar grid. Okay, and if you notice, the black dot in the middle, that is our pole. And then we can see, just like the unit circle, sorry, we start with 0, pi over 2, pi, 3 pi over 2, and then if you want 2 pi. And we can label these rings 1, 2, 3, 4, 5. So this is the polar equivalent to doing a 5 by 5 XY grid. Okay, so this is the same as something like this: 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So these two things are basically the equivalent, just one is rectangular and one is polar. Okay, so we are just kind of going through and creating a graph. So our point, okay, or our function, okay, this first one is just simply theta equals pi over 4. Notice there is no r value. So think of this just like a vertical line or horizontal line where it'll say something like x equals 3 or y equals 5, right? We're not given that other variable, which means that other variable can be anything, and this equation is still satisfied. But always, theta must be pi over 4. Every single time. Negative 1, negative 2, 2, 3, 4. Okay, so we are at pi over 4. Sorry. There we go. A little tricky at the bottom. Negative 1, negative 2, 2, 3, 4, right? If we connect those, we can just see that that is actually just a line. Okay. Look at this next one. R equals 3. So we're told that R equals 3. We have no information on theta. So theta can be whatever we want. So in this graph, we're giving it in degrees instead of radians. So we want to make sure we're in degrees. So 0, say 75, 180. Let's go 225, 270, 345. But R is 3, 3, 3, 3, 3, 3. Every time R is 3. 0, 0. Sorry, 3s, not zeros. 225, 3, 3, 3. And if you notice, this is just circle with radius 3. Okay. Now, what about this crazy thing? This is a much more challenging thing to graph by hand, but we'll give it a shot. And what we'll do is I want you to really use your calculator to also um, reevaluate this. So use your calculator to graph this right here. To do that, you're going to need to change the mode, right? So if you remember in the last video, we changed our mode from function to parametric. You're going to go mode. You're going to go down. It's about the fourth option down usually. You should see FUNC, then space, then PAR, space, POL. So it's function, parametric, polar. There's another one that's SEQ for sequence, but we're not using that, so we're just polar. Once you get there, quit. Go to your Y equals menu, and you see there's R1, R2. If you watched the meeting video or were at the meeting, you saw me do this on the virtual calculator, so it should be pretty comfortable on what to do. Now, depending on what mode you're in, if your calculator is in degree mode or if it's in radian mode. But either way, when you do this, if you go to window, you'll see a thing that says theta min, theta max. Depending on what mode you're in, you want that window to represent one full rotation. So if your calculator is in degree mode, your theta min should be 0, your theta max should be 360. If you're in radian mode, then your theta min should be 0 again, your max should be 2 pi. So make sure that you have that set so that way you can kind of get the full visual of what happens in one full rotation. Since arbitrary functions repeat after that, if we made, say, theta go from 0 to 4 pi, so 2 full rotations, or negative 2 pi to 2 pi, it's just going to basically highlight over this thing over and over. So let's throw in some nice simple angles here. Okay, let's throw in some 0 degrees, 60 degrees, 120 degrees, 180 degrees, 240. Let's go 300, and let's tack on one more. Let's go back to 360 just to make sure we end up at the same spot. Now I'm going to leave some of this math up to you because, quite frankly, at this point in the term, this should be very easy calculations. 2 plus 2 times cosine of these angles. All of these angles fall on the unit circle. You should be able to very quickly and easily figure these out. But we get 4, 3, 1, 0, 1, 3, 4. And so what that looks like, okay, is it looks kind of like this. And now, as you look at these angles, the way they go, it's kind of cool. It actually gives us a direction that this graph goes. And so it starts at 0 degrees and it kind of goes, let's do this in red. Comes this way. And then what it actually kind of does, it kind of comes around here and then taps into the middle, and then it kind of bounces out almost. It looks like this. And so we actually get a direction, just like we did with parametric equations. And it looks kind of like that. You should see something very similar in your graph. You should see this kind of tuck in here at the pole from that negative side. Awesome. Look at this one here. 3 cosine 2 theta. Now here's what I'm going to do on this one. I'm going to let you do it because this is not something I'm going to have you graph by hand ever. This is absolutely something you will need to graph on a calculator. And so what I want you to do right now is I want you to pause this video and graph this on your calculator and see what it looks like. Okay, go ahead, pause it. We'll come back. All right, welcome back. So if you do this, right, let's make our jumps. See here, our table, if you want to, let's go 0, right? This is radians. We're going to do radians. Notice our plot over here is in radians. 0 pi over 12 pi over 6 5 pi over 12 pi over 2, okay, 2 pi over 3, 5 pi over 6, 13 pi over 12, 5 pi over 4, okay, 17 pi over 12, 3 pi over 2, 5 pi over 3, 11 pi over 6, 23 pi over 12, and that takes us right up to the edge of a full rotation. Now, you may be asking yourself, why am I choosing these numbers? And it really comes with just an asymmetry that I'm going to show. If I were to give you this problem on, say, a test or something like that, I would absolutely fill in these theta values for you and just have you kind of doing this. But quite frankly, I don't care. This is just a very simple, basic calculation of evaluating a cosine function, which is something that you should be comfortable with since chapter 6 at the beginning of the term. Not really something I'm testing you or worrying about right now. Okay. And honestly, this is all calculator work that I'd be having you punch on your calculator, and this is just tedious, non-necessary things. I'd rather be able to see that you can get this graph. Okay. But we have 3, 2.6, 1.5, negative 2.6, negative 3, negative 1.5, 1.5, 2.6, 0, negative 2.6, negative 3, negative 1.5, 1.5, 2.6. And then if we did do a 2 pi, right, we'd get back to 3. So the way this looks is very strange. Okay. The way it works, so let me get these distances right. 1, 2, 3. Okay. Ignore my terrible artistry here. Okay. This is definitely not a mark on anything but my terrible artistic ability. Okay. So what it roughly looks like is it starts out kind of going. Let me. Okay, so it starts out coming from here, from here, down to here, and finishing like this. So while this is all a very terrible drawing of what actually happens, hopefully you guys kind of pick up this shape. In mathematics, we call this graph the four-leaf rose. Right? If you look at that, everyone looks at that and sees a rose, of course, right? It's obvious. That's why I drew it in red, right? But we can definitely see the four leaves of it. And because mathematicians like to make things prettier, we call it a rose. So that is how we graph this one. Now let's talk about how to graph something like this. If you notice, your calculator only has r equals, right? So if you look at the y1 or y equals, it says r1 equals, r2 equals, r3 equals, right? So that's just kind of equation 1, 2, and 3, and so forth. That's where the numbers come from. But it's just r equals. how do we do with r squared equals? And what we have to do is we have to solve this equation for r. And you're like, well, that's not hard, right? But what ends up happening is we actually end up with two equations. So r squared equals 1 over theta, right? We know just square root both sides. It gives me r equals, but that gives me r equals plus or minus the square root of 1 over theta, right? And if you are one of those and you'd like to, you can. It's plus or minus 1 over square root theta. So what does that graph look like? Well, I don't want to get too crazy with you, but it kind of does this weird thing. It wraps around itself. Depending on what your angles, it gets crazier and crazier and stuff like that. It's kind of a cool graph. So take a look at that in your calculator. Ignore my terrible artistic ability, because this piece here does not actually start right there. It does, more kind of like what that other side does. Like that. So, all right. Now, about this next one. So you can use your calculator and graph this and see it's kind of a cool little thing. But I want to focus on how do we rewrite this in rectangular form, because that's really the important piece. Okay, how do I rewrite this in rectangular form? I can guarantee you I will give you a question like this on the test. So for those of you watching still and paying attention and actually focusing, right? If you're watching this for one of my classes, I guarantee this will show up on a test. How do we use a calculator to graph, or not how do we use a calculator? That's easy. How do we rewrite this in from polar to rectangular form? And what we're really looking for is we're looking for ways to find an x and find a y. And if you remember, okay, x is equal to r cosine theta, y is equal to r sine theta. So I need to find that. And the easiest way to do that is to, first of all, get rid of these fractions, right? No one likes a fraction. So we're going to take our equation, our r equals 2 over 4 cosine theta minus 3 sine theta. And I'm going to multiply both sides of this equation by 4 cosine theta minus 3 sine theta. And we all know what happens. That goes away. And now, just looking at what I have, right? I could rewrite this in another line, but I'm going to pause for a sec because you guys are intelligent algebra workers, right? I can see that I could take this r and distribute it. And if I do that, I end up with 4r cosine theta minus 3r sine theta equals 2. Ooh. And look at that. That is x, and that is y. So by substituting in that x equals r cosine theta, y equals r sine theta, we get the equation 4x minus 3y equals 2. Now, if we're doing it in a rectangular equation, right, technically, yes, that is good, but we always like to get things in terms of y equals, and so we're going to do the same thing here. So subtract 4x from both sides. That cancels. And we are left with negative 3y equals negative 4x plus 2. So we just simply divide by negative 3. Y equals, now if you remember, right, when I have addition like this and I'm dividing by one thing, I can actually divide each piece. That's just kind of like splitting up a fraction. And so I get negative 4 over negative 3 gives me a positive 4/3 x. 2 over negative 3 gives me negative 2/3. Hey, this is just a line. This is very simply just a line. So this polar equation of r equals 2 over the quantity 4x or 4 cosine theta minus 3 sine theta is all just giving us a line with a slope of 4/3 and a y-intercept of negative 2/3. That's it. It's not crazy. It's not too hard. It's very nice and simple. So now here we're going to look at something. We're going to let r1 equal 3 and r2 equal 2 plus 2 cosine theta. These are two different polar graphs, and I want to find where do they intersect. Well, what we're really looking for is, if we imagine these, right, the r1 and r2 kind of throws us off. Because these equations, the 1 and the 2 are really just subscripts for kind of equation 1, equation 2. What we really have is two equations. That's r equals 3, r equals 2 plus 2 cosine theta. The subscripts are irrelevant. So I have two equations that tell us what r is equal to. To find out when they're the same, I simply have to find out when they are equal to each other. So I can take this and solve very simply 2 plus 2 cosine theta equals 3. So subtract 2 from both sides, giving me 2 cosine theta equals 1. Divide by 2 on both sides. And we get cosine of theta equals 1/2. And now, being the brilliant trigonometric minds that you guys now possess after all this time that we've worked with these things, you should see an equation like cosine of theta equals 1/2 and be like, ha ha, unit circle, let's look at that thing. I know that cosine of theta on the unit circle is simply asking for the x value. I know there's points on there that have x values of 1/2. So we find those angles and we see that theta must equal pi over 3, or if you go a little further around the circle, 5 pi over 3. And that's it. That is how we solve a polar equation. So that's it for this section here. I hope you guys understood what we talked about, right? The biggest thing here to kind of really pull and take away were those couple equations for polar to rectangular, being able to utilize those. Otherwise, it's just really a cool, fun application of all of your lovely zoom in rate. So this right here is the big kind of takeaway thing that you should have written down on your formula sheets, right? But otherwise, it's just a nice, cool application of all of these trig things that we've dealt with, these ideas of unit circles and stuff like that, and going forth from there. So with that, I will see you guys for our next section, which is going to be actually 10.1. We are skipping chapter 9, and we are going to work on parabolas. Like, parabolas, that's a quadratic. We've already done that, right? Aha! But have we done all of it? I'll see you next time.